Okay, so let's use maximum shear stress theory to determine the smallest diameter. So what we have is tau allow is 50 megapascals. We have journey bearings at A and B, the transmission of power to and from the shaft. The belts and the pulleys are subject to tension as shown. Find the smallest. All right, cool. So here's our sketch, all right, for the problem. And what we'll end up having is we'll get something like this. And I'm going to show you how to find all of these. And then we'll do the shear and moment diagrams and the torque. Okay, so let's go right ahead. And what we need to do is we need to look first. Let's do some sketches. We're going to find reactions at A and B. Okay, so let's draw, and we're going to look at the, I'll zoom out just a tad, first the Z Y plane. Okay, so we're looking at, let's do it in highlight, this plane. Okay, so what do we have? Well, we have up, we'll call AZ. See how it's 550 and 400? Those actually add up. So that's 950. We have a reaction at Z, we'll call BZ. And then this 300 and 200 do not act in this plane. They're in the XY plane, and we'll do that here in a second. So what we can do is we can sum the moments at A, set it equal to 0, assume that way is positive. Okay. So what we're doing is we're rotating around the x-axis. So we have BZ times 0.5 meters minus 950 newtons times 0.25 meters, and we got 0. So BZ becomes 475 newtons. Then we can sum the forces in the Z, set it equal to 0. We have AZ plus BZ minus 950 equals 0. And we get AZ to be 475 newtons as well. Cool. Okay, I'm going to do it right here. Let's now look at the XY plane. So we have AX. Over here now we have BX. And then if you look here, they're going the same direction. They add up to 500. So 500. Okay. Again, we'll sum the moments at A, set it to 0, plus moment that way. So this way we're going around the Z-axis now. Negative BX times 0.5 meters plus 500 times 0.65 meters equals 0. BX equals 650 newtons. We can sum the forces in the X, set them equal to 0. Up is positive. We have AX minus BX plus 500 equals 0. And AX becomes 150 newtons. Great. So let me just put those in. 150, 650, go over here. AZ was 475, and this is also 475. All right, cool. Now what I'm going to do is I'm going to do the shear moment diagram. So let me just move these. These are already done, but we can look at those after. Okay. Boom. Let's do it right there. Okay, so shear and moment diagrams. I'm going to go down. And what do we have? We also have to label this at C, and then this is D. And I will label this right here roughly C, and then this is D. Okay. So 475, that goes up to 475, right? And then it's going to go over to C, which is here, right? If I do a dotted line, it goes down 950 to minus 475, because at this location right here, it comes back up. Okay? Cool. I might as well do, I'll do them together. And I'll do dotted line, that's C and D. Okay. So here we have 150 goes up all the way to B, right? And then it goes down to here. This is negative 150. Oh, sorry, 500. I meant to say minus 500, right? Then it goes over, and then it comes up. Let me close this, and let's fill this in. There's our shear diagram. You can label V, newtons, V, newtons. Let's go down and let's do our moment. I'll extend that, do that here. Go over. Okay. Moment over here. It's going to start right here. And then it's going to go up to here. And then it's going to go back down. Okay. Going to be the highest at C. And this is 118.75. How is that found? By taking 475 times by 0.25. There's our moment diagram. Over here, what we have starts here. Going to go up linearly, right, to here, and then it's going to go down. Oh, I didn't quite get that. That should be over more. Right there. And that's 0. There's our moment. How is this found? This is 150 times 0.5. That maximum value is 37.5 Newton meter. So here's our moment diagrams. Right? Also, if you want, you can look right here. That value is, oh, sorry. This is 75. I didn't mean to do that. This value right here, 37.5. Sorry about that. Okay, yep, that should be 75. Okay, there's our shear and moment diagrams. Let's do a torque diagram. And I'll just do it right here. Here is a, actually, you know what? We'll do it right underneath this one. It doesn't matter, just to be consistent. Okay. So what we have is, this is where C, right here. So right here, this is C. We've got torque there. Okay. And then we also have this torque here at D, right? Because if I draw, let me do it in black here. This is that shaft. This is A, C, B, and D, right? Okay. Let me keep consistent here. I'll do it as a black color. Oops. So how do we find the torque at C? Well, you take 550 times 0.05 minus 400 times 0.05, and you get 7.5 newtons. Torque at D, 300 times 0.075 minus 200 times 0.075, and this torque becomes 7.5 newtons as well. Now, the reason I did it like that is if we go to the diagram here, right, this is 550. It's going to pull that way. That's the torque. Here, it's going to go that way. That's the torque at D. Okay? And you take your 550 and you multiply it by the radius of that sheave for both cases. Okay? That's why it's 0.05 and 0.075. So how does this look? Well, it's going to go down because it's going that way. It's going to come up over there. And this is negative 7.5. So this is your torque diagram. Okay. So, which is also over here. Okay. Just a little bit better for you. Now, we have to do that. We can now solve D. And D is 2 times C. And we can rearrange that shear distortion energy equation to solve for C. 2 over pi times tau allow times the square root of m squared plus t squared, and this whole thing is to the 1/3. Okay. Now, what you need to do is you need to find the maximum moments in both of these and figure out where the maximum magnitude occurs. There's 2 critical points. C, right? So this point right here, which is at C, and this B here, which is 75. So what we're going to do is we're going to look at 2 cases. We're going to look at moment at location B and the moment at location C. So MB is the square root of mx squared B plus mzb squared. What we have is there is nothing here, but there's 75 here. So this becomes 75 Newton meter. Over here, it's mxc squared plus mx, at C. Sorry, these are at C squared. And this is actually the z direction, right? Okay. MC becomes the square root of 118.75 squared plus 37.5 squared, and you get the moment to be 124.5 Newton meters. So these were these are the moments in both of those shear diagrams at each location, because you need to use, this is going to be M now in this equation. Now, wherever this M applies, it's at C. The torque at C is what you use, okay, which was 7.5. So you're going to use that torque at that location. So now we can plug everything in. C becomes 2 over pi times 50 megapascals, right? You got to convert that, times 124.5 squared plus 7.5 squared, and this whole thing is raised to the 1/3, gets 0.0117 meters, and therefore the diameter is 2 times C, 2 times 0.0117, and the diameter becomes 23.3 millimeters, or I would use 24 millimeters. So, in summary, for this case where you're using maximum shear stress theory, what you need to do is you need to split this up into like 2 2D views. We have the ZY plane, the XY plane. Find your reactions. Find your shear and moment diagrams. Find your torque diagram. Figure out where the maximum magnitude for the moment occurs at whatever point. find the magnitude, use that, and then wherever that acts, that location, that's where you're going to use the torque. Then you can plug it into the shear stress equation. Okay, thank you.